For years, the industry has addressed capability gaps in AI through a single strategy: make the model bigger. More parameters, deeper stacks, wider contexts. This brute force approach eventually hits a wall. The first predictable failure is economic. As models ingest larger inputs, the token and compute costs begin to scale exponentially. Following the costs are massive spikes in latency. Processing times elongate because the delay is directly proportional to the physical size of the model attempting to parse the data. Then the outputs degrade. Hallucination risk scales alongside context length. The more raw data a single model must hold in its memory, the higher the probability it fabricates a connection. This leads to the lost-in-the-middle phenomenon. Deeply buried, highly relevant information is ignored because the monolithic input overwhelms the model's attention mechanism. These failures stem from the industry's baseline assumption that one model should handle everything. Continuing to add parameters and context to a single monolith guarantees structural breaking points. Solving them requires a complete architectural pivot. This framework breaks the monolith into 3 stages: perception, inference, and generation, connected by learnable interfaces. Bridges act as mathematical contracts with strict compute budgets. They isolate tasks, ensuring models handling perception and generation receive only the specific data they need, preventing system overload. In 2025, a production implementation of this RAG architecture achieved sub-0.3 millisecond sidecar latency. Because the bridges filter data so aggressively, the system realized a 97% compute cost reduction on input tokens. In production testing, these structural constraints resulted in a 0% hallucination rate on grounding tasks. The effective architecture of a multi-stage system is defined by the learnable interfaces connecting its specialized models, rather than the scale of the models themselves. The production results we see in 2025 are the direct execution of theoretical equations mapped out in 2018. This is equation 6. It defines the differentiable composition of the entire architecture. It wires 3 distinct neural modules together using 2 intermediate bridges, GAB and GBC. The process begins at the perception stage, FA. This module takes the raw user query and the entire document memory to generate a semantic representation of the request. That representation hits the first learnable bridge, the GAB sidecar. This bridge acts as a filter, aggressively narrowing the perception stage's massive output before it reaches the inference stage. Equation 13 shows that multi-stage systems multiply several Jacobian terms. These bridges act as the primary conditioning levers, ensuring gradients flow correctly and protecting upstream representations from downstream noise. Equation 6 proves that without these strict stability constraints between stages, a multi-stage system will collapse during the training process. To maintain stability and meet its tight compute budget, the sidecar bridge must compress data aggressively. This is the information bottleneck objective, equation 11. It forces the bridge to minimize its mutual information with the raw input, while maximizing its mutual information with the target output. In practice, the system discards the document haystack and passes forward only the specific text spans that mathematically predict the correct answer. This reduces thousands of input tokens to roughly 100 to 300 tokens of pure signal. The information bottleneck ensures the generation model receives only the exact evidence required, altering the economic limits of the entire system. These mathematical bridges are instantiated through specific engineering typologies. For retrieval and span extraction, we use an attention-style bridge. This diagram shows the 2 main options. On the left, the attention-style bridge dynamically queries the document memory sequence per request. On the right, the residual bridge uses an identity path to guarantee safe gradient flow and protect against initial training collapse. The residual bridge is the safe default for stability, especially when you are fine-tuning a pre-trained stage. The dynamic attention-style sidecar, however, is necessary for retrieval. In production, this bridge is constrained by a severe hardware limit. It must execute span extraction in under 0.3 milliseconds. Designing these bridges forces engineers to choose between high-speed dynamic querying or stable baseline communication based on the task boundary. Multi-stage architectures look like a slow sequential chain on paper. In reality, they execute significantly faster than monoliths. This is the event-driven execution model. The critical path, embedding the query, extracting spans, and generating the answer, operates without waiting for auxiliary tasks. While the sidecar extracts spans in sub-0.3 milliseconds, authentication, request logging, and semantic caching execute concurrently on parallel tracks. Equation 21 models the compute decomposition, showing that the final generation model always dominates the total cost. But the sidecar's aggressive span compression slashes the input size fed into that generator by over 97%, collapsing the primary compute bottleneck. Think of the generator like a DJ waiting for a set list. The system prompt is already cached. The model is pre-warmed and idle. The instant the sidecar delivers the compressed spans, the generator begins streaming immediately. Event-driven execution shows that optimizing the upstream interface mathematically collapses the exponential latency costs of the massive downstream generator. This architecture addresses hallucination at the structural level rather than through post hoc guardrails. Monolithic models typically hallucinate when they attempt to fill gaps in context, confuse separate documents, or ingest irrelevant noise alongside facts. This is the information theoretic denoising limit. The bridge optimizes the bottleneck, scrubbing irrelevant noise before it reaches the generation model. The final Q-LoRa bridge conditions the generator to speak only this pure signal format, ignoring anything outside the provided evidence. By structurally deleting irrelevant context, the system removes the primary catalysts for grounding errors. In the 2025 production implementation, this structural isolation resulted in a 0% hallucination rate. The 2025 production results validate a theoretical framework that once sat in the shadow of monolithic scaling. The metrics are definitive: 97% lower token costs, under 0.3 millisecond latency, and zero grounding hallucinations. The math from 2018 was correct. The industry was simply waiting for hardware to catch up and allow for these microsecond compute budgets. The mandate for building AI capability is to design the interface constraints between models first. Engineered correctly, stage performance naturally follows. The era of monolithic LLM scaling is reaching its limit. The future of systemic capability is dictated by the engineering of its internal bridges.